Yeah, thanks. Thanks very much for the warm welcome as always, Gareth. I'm just resharing the slides for Dan and Tom to come on and present. Yeah, really excited to have Dan and Tom from RWE. They're some of the leading experts in the field, and today's presentation is going to be on solar farms and batteries. So without further ado, Dan, Tom, I'll pass over to you.
Thanks so much, Rachel. So quickly, just to introduce myself, my name's Dan Corcoran. I'm a development projects manager at RWE, primarily focusing on TCPA applications from once we've got grid secured, land secured, and then take it through the planning process and ultimately hand over to conditions. And I'll just pass it to Tom for 10 seconds to introduce himself.
Hi all, my name's Tom Johnston. I work in the same team as Dan, but I work on the sort of taking it from once it's got planning permission to realising it and building it out. So from sort of the route to market for the solar and the batteries side of things.
Cheers, Tom. So just to give you an insight to who RWE are and what we're doing, we are the UK's largest energy provider. We make 15% of the UK's energy generation, so that's about 14 million homes that RWE power across all of our energy portfolio. At the minute, we've got just under 5 gigawatts of renewable energy installed. We've got a pipeline for another 5 gigawatts of just solar. That's excluding our offshore wind, onshore wind. And we're currently looking at a pipeline of 2.5 gigawatts of battery capacity as well. So as a company between now and 2030, we're looking to spend 15 billion to invest in renewable energy as we transition away from traditional generation. So we're coming at this from someone who's heavily involved in the industry and really see batteries as a solution to help us use renewables better. Next slide, please, Rachel. Okay, so just to give you a bit of context as to where we are with UK energy storage. As this is as a whole country, we're at about 4.3 gigawatts that we have installed, and we're looking to have around 30 gigawatts by about 2030. And that's going to really help us store renewable energy when it's generated, where it doesn't match where demand is on the grid, which is what conventional power could do. You could just turn on gas, coal, whatever, where it was neat when you wanted it, but we can't do that. We can't ask the wind to blow or the sun to shine at the right time, and batteries really is going to help us manage the system better. Next click, Rachel, please. So yeah, how are the batteries really going to help us with renewables? If we could go to the next slide, I'm going to talk you through a simple 24-hour day from a solar perspective and how batteries are really going to help solar help the UK move towards its renewable targets and manage the wider energy demand across the country. In yellow here, what you can see is a very typical bell curve of solar. Now, this could be the middle of winter, could be the middle of summer, but what you're seeing on the yellow on this bell curve across is that the sun rises, maximum solar generation, and as the sun starts to set, solar generation is going to taper off. What's brilliant about solar is that it's forecastable. You can predict that any given day the sun will rise and the sun's going to set. And even if there's clouds in the sky, you're still going to get generation occurring. So it's a very forecastable bell curve. The problem with that is that it doesn't always match the bell curve of demand, of where people wake up in the morning, start cooking breakfast, have electric showers, heating, and the same in the evening. But it does help during the daytime use and how we can match that use to what people, when people are using energy. So really early in the morning, at the bottom, you can see the timeline for a 24-hour day. During, say, 2 to 4 a.m., energy on the wholesale market is quite low. There might be offshore wind turbines spinning, onshore wind turbines spinning, but people aren't awake yet using it. And what that shows is that you could charge up these batteries. Batteries which are on site could take the energy as it's being made from wind or any other sources and actually store it. But then you move into about 5, 6, 7, 8 a.m. The sun's starting to rise, so you start to see solar begin to generate and help the grid. And the dark blue there, or the black, is where the batteries are then discharging. With the batteries from all of that generation overnight that wasn't being used because people were asleep can now actually be discharged onto the grid and then actually meet the peak morning strength of demand. Throughout the day then, the solar is generating, and around lunchtime, there's going to be lots of sun, but maybe people are away from their computers, so they don't need to be using as much energy because they're on a lunch break. Maybe the sun's heating their housing, so they haven't got electric heating on, and there's an excess solar being generated compared to where the demand is. So we can start charging the batteries again. You can use that energy and say, well, the grid doesn't need it right now. Let's move that onto the batteries for later. As we move into the evening, again, we can start charging the batteries if there's any generation that's excess coming off from offshore wind, onshore wind, or elsewhere just on the wider energy network, because it's all connected. And then you get to the evening and we can start discharging again when people are doing homework with the kids, cooking dinner, having showers, heating the house. So really helping to balance where there's an offset between different sources of generation or solar, which is very forecastable, to help try and meet different peaks of demand across a 24-hour period. So that's a very simple way of just how we can help this load shifting that we see. You might see two different types of solar farms as you that have batteries, as you're coming at it from a council perspective. And this is what we kind of call between DC located and AC located. So you may see one design where you have the solar farm and you have a concentrated area, couple of acres, where you're saying all of the batteries are going there. And you may see other designs where you have batteries that are spread out across the site, and there's batteries roughly maybe one every 10 acres. And there are two different ways of you can have a design for batteries to be paired with your solar. Now, just to very simple, what is the difference? On the left-hand side is we have here, which is the DC coupled. What that's showing there is that the energy can be generated from the solar panel. It then goes to the point just before the national grid, and it says, do we need it on the grid or not? And at that point, a decision can be made. And if it's not needed, it could then go straight into the batteries. When you're looking at battery compounds, that's AC located. And that means that what's happening there is the panel that makes DC electrical energy has to go through an inverter to make it into AC, and then a decision's made about whether it goes into the grid. If it's not needed at the grid at that moment in time, it then has to go back through an inverter to make it back to DC to go back to the batteries. Now, this is very suitable for some types of layouts, some types of grid connections, and some developers. It's not to say that there's a right or wrong way. They're just different ways of designing a particular electrical generation facility, but it just shows you that there's two different ways that it could be as we move forward, whether you have a single compound or you have it dispersed. It's all about how you use the inverters and the decision-making process about when the energy would go onto the grid. Next slide, please, Rachel. And I'll hand it to Tom now to talk about this need for energy transition.
Great, thanks, Dan. Yeah, I think that's really interesting to sort of see that shape of sort of solar across the day and how the batteries can trade around it. Obviously, this is also the same for wind. Wind has a different shape. It's maybe a little bit less predictable, but still, there's very good forecasts out there nowadays. But just a bit of a general overview of like the UK targets and look at this from sort of a macro perspective. Offshore wind, they're planning now 50 gigawatts by 2030. I think solar, they're sort of saying they're tripling it. So they're probably looking at about 45 gigawatts by 2030. Some big ask and a lot of generation coming on the network, which is great to see on a way to sort of net zero. What's clear here is that with this generation volume coming on the grid, there's going to be periods when it's windy, very windy, and we're overproducing energy. And there'll be periods when it's really sunny and we'll be overproducing solar energy as well. But then there's also obviously periods where the sun's not shining or the wind's not blowing, and we need to meet demand on the grid. And at the moment, in terms of flexibility, it's gas that's turning on. Coal used to be used, but now it's obviously turned off since about 10 days ago, which is good. But yeah, basically at the moment, gas engines, gas power plants across the country are turning up when the sun goes down or the wind stops blowing. So what batteries can do is they can replace that form of flexibility, so they can sort of decarbonize that part, that sort of last part. So that's a great thing. So what batteries will do is they'll take that energy, they'll move it across into the evening peaks, as sort of Dan said already. And it's actually quite nice to see that already, sort of in 2024, with all the renewables that are deployed already, there are some days where we're seeing that renewables are meeting all demand alongside sort of nuclear and hydro and some other things with very, very little gas generation actually running. So that's really good to see, and that gives us a little insight into what we'll see happening more and more often as more renewables come online. But batteries are not just for time-shifting renewables, they're also very good at providing other sort of ancillary services to the grid. So one of the things that they can do obviously as well is provide capacity. So they're there, dispatchable plant. If they're charged up and there's the system's tight, they can provide energy to the grid through the sort of capacity market mechanism. They also are very fast responding, so they're able to sort of regulate the grid's frequency very well, which is a critical service to ensure keeping the lights on. And that's something that's, renewables, people always say, intermittent, they fluctuate a lot more. That's where batteries can really firm out renewables well. And actually the fast acting nature of them is much more beneficial for the grid compared to sort of coal and gas plants, which are slow to warm up and slow to turn down. Next slide, please. Great. So this is just a day in August this year, actually, that happened. So the top graph shows the generation profile in the UK for, I think, 4 days or so, from sort of Saturday to Wednesday. You can see the sort of legend at the bottom, which shows the different generation technologies. You can see solar is a bit more, you can see the time of day easy enough on that, the sort of bell curve that Dan was talking about. Onshore wind is the light blue, offshore wind is the dark blue, and gas is the grey on the chart. Those are the sort of three I think I'll point out as quite interesting. So what we see is that sort of Saturday, Sunday, generally lower demand, but it was nice and windy and sunny at the same time, and we were able to offset all the grid on the all the gas on the grid during these periods. And actually we were exporting through interconnectors and charging batteries during this period. So because renewables are zero marginal cost generation, so there's no fuel that goes into it, there's no carbon cost to that. They're able to generate when as low as zero, and in some cases prices go negative. So these are good opportunities for the batteries to charge when it's nice and cheap. And then what we see then happening is when the wind, the sun goes down and the wind sort of tails off a little bit. You can see that just before, sort of Monday evening, the gas then has to turn on in the UK at the moment, and then that drives up the price of electricity. And that's what then we have to pay. So what batteries can do is they'll charge from that excess energy, cheap energy, because there's no cost to making it. Once you've built the panels or built the wind turbines, they'll generate, and then offset that gas demand in the future as more batteries come online. So batteries are sort of that way of taking renewables, firming them out, and squeezing off that last bit of sort of conventional fossil fuel generation on the grid. That's me, I think. That's back to Dan.
Cheers, Tom. And yeah, I think just as Tom was saying, the ability for batteries to respond quickly was demonstrated just a couple of days ago, where we had an interconnector fail in the UK, and within seconds the batteries can just start discharging, whereas in times gone by that would have meant regional power cuts. And I think it's interesting to see that the more renewables really does mean that as these compound, we are genuinely looking at lower prices, and that's what we're seeing on wholesale markets, that it really does lead to a tangible difference for consumers. Now, one side I wanted to finish on was battery safety. This is something that we see a lot of concern from members of the public, from local authorities, and I think one thing that's really important to stress is the batteries that we're proposing today and would ultimately be building are not the same batteries that are already in existence that were there many years ago. We're not comparing apples and apples anymore. One way that I like to use a very oversimplified analogy is that in times gone by, if you had, say, a big battery cell, that could be 100 units or 100 different batteries, and that could be into 10 lots of 10, say, AA's. Now, that was just monitoring in years gone by. You would monitor the whole 100. Then as technology improved, you would monitor 10 lots of 10. Now technology is even better, that you're monitoring on cell level data. The temperature of the individual battery cell, you're monitoring the ability for it to charge and discharge, and it's comparing it against each other cell, so you can spot any error within a wider battery pack by constantly analyzing across the units. As well as using liquid cooling, lots of remote isolators, so the second that you'd find a single deviation, there's automatic switch offs rather than needing human intervention. Site information points, where we're working closely with fire and rescue authorities, where we're giving the what 3 words for each battery locator, showing them the manufacturer's requirements. Also, newer batteries have a higher operating temperature, which means that higher safe operating temperature, which means that if they can safely operate to a higher temperature, then on a hot summer's day, if energy was needed and they are running, by being able to safely operate within that higher bandwidth, compared to saying they must safely operate up to say 30 degrees, giving them a higher temperature means that there's less likelihood of failure. There's many internal suppression devices, whether it is oxygen reduction kits, whether it's spark inhibitors, anything to try and reduce the likelihood of any type of failure. We're also looking at DC coupled across the market where that can be done, because it means the batteries have wider spacings between them. But it's not something that can always be done, but it just offers greater spacing. And as on the bottom image, as you can see, there's panels that are deflagration panels that allow any internal pressure or any gases which are coming off to be expelled, and they can close again to regulate what's happening within the unit. As it's a sealed unit as well, they're then looking to be IP66 rated, so that they can be waterproof and not have any rainwater contact with any cells. Should there actually be a failure event within the unit, it can just be very quickly shut off with the early detection devices, therefore makes it safer for operators and fire rescue service to then handle any event. So I appreciate that was a very quick run through from me and Tom. There was an awful lot of information in a short amount of time. We are here for any questions that you might want to email us afterwards or ask specifically about, but also welcome the floor and would like to pass it now back to Rachel.
Thanks very much, Dan and Tom. Yeah, that was really, really interesting. And you're right, you did cover a lot, but it was really clear. So thank you so much for putting that presentation together. So
this kind of touches on what we were discussing at last week for the site selection. And happy to go into more detail after that with that PowerPoint as well. But fundamentally, when you look around the country and you see each substation, each overhead power line, each pylon,